Good afternoon and welcome to the CERIAS Computer Security Seminar from Purdue University. Today our speaker is PhD student Weining Yang, and he is working with Professor Ninghui Li. His topic today is on the issue of privacy and electricity metering, load profile data that utility companies can gather from electricity meters. Some of the fine resolution of that data reveals information about the customer. So today's topic, minimizing private data disclosures in the smart grid. Weining?
Okay, thank you. And good afternoon, everybody. So today I will talk about minimizing private data disclosure in the smart grid. So to begin with, I will give you some brief idea of what is smart grid. So smart grid, actually people sometimes call it smart meters because smart meter is the main component of the smart grid. And smart grid is something, it's electrical grid that can use the information and also can act on this information. So for this information, smart meter is the component that can collect these informations. So in the rest of the talk, I will mainly concentrate on the smart meters. And also I should give you some idea what is the smart meter. So the term smart meter here often refers to an electricity meter, but it can also mean a device measuring maybe natural gas or water consumption. So we also call smart meters real-time meters or near real-time meters. That is because smart meter can record data with a pretty high frequency, let's say 1 second or 1 minute. So if you get the data, it will pretty similar to the real-time usage. So that's why we call it real-time meters. And in contrast, we also listed the conventional meter here. So the conventional meter, we also call it interval meter or time of use meter because it can just record the total consumption for some period of time. And another feature for the smart meter is it can transmit the data use the wireless network, and that's the difference of the smart meter and the conventional meters. So nowadays there's a lot of implementation of smart meters, and here's just some examples in the United States. So we can see here from 2006, so in California there are already 9 million meters. There's a plan for 9 million meters to be installed in Northern California. It starts from 2006 and the plan is for 5 years, so I guess it has already been finished now. And for Austin Energy, it's a it's a national 9th largest community electricity utility, and it also wants to deploy about 26,000 smart meters. And to see something closer, there's an example in the CPS Energy. There will be about 40,000 meters. And actually, there's more and more smart meters all over the world. So here's some example countries that has already started their smart meter program. And in these slides, I listed some countries. They haven't started the program, but they have the plan for the smart meters. So the thing is, we can see smart meter is really popular these days. But why people like smart meter? And here I will give you some potential benefit for the smart meter. So first, for the utility company, they want smart meter. The main reason is that using smart meter, they can set different prices for consumption based on the time of day and the seasons. So based on that pricing policy, they can encourage customers to adjust their consumption habits to be more responsible to the market. So for example, they may reward the customers who shift the energy usage to the off-peak period. And by doing this, they can balance the consumption usage to some extent. So basically what they can do is when the electricity usage is high, they set the price to be high, so customer will not willing to use the electricity at that time. And when the price is low, when the electricity load is low, then the price may be lower, so more people will try to use the appliances at that time. So for that reason, we can see that the result of that is the maximum electricity load can be lower. So that's what the electricity company wants. By doing this, what they can do is they can construct less additional generation, or at least they can purchase less energy when the price is high. So another potential benefit for the utility company here is they may try to eliminate some jobs, because as mentioned before, smart meters can use the wireless network to directly transmit the data, so there's no need for a person to collect data and something. And also for the customer, there's also some benefits. So the first benefit is they can estimate their bills. And actually, this is the major source of the complaints for many customers nowadays. And also, the smart meter can be a good tool to help the customer to better manage their energy use, because the smart meter can give them real-time data. So from this data, customer can know that at what time they have some high level electricity usage. So they may know that what appliances is energy costed. So if they want to reduce their bill, they may be able to switch their usage of their data appliances to some low time period of time. So by doing this, basically the smart meter can help people to manage their energy use and reduce their energy bills. Some interesting thing is, so from the previous slides we can see smart meter is actually some promising new technique that can help people a lot. But here's some interesting thing. So just this afternoon I tried to search the smart meter, this term, on Google. And then you can see the first result is from Wikipedia, that is not that meaningful. And for the second result, we can see it's just some complaints about the smart meters. So it seems that people do not like smart meters, right? So here's it's a screen. It's just a figure of that web page. So we can see people listed a lot of drawbacks of the smart meters here. And actually, if we read the result further, we can read the top 10 results from Google. It's just for smart meter. And we can see 7 of them are negative results. So they think smart meters are bad things. And just 3 of them, I use green circle to illustrate it's some positive results. And actually, the first result, it should actually not be said positive because it's from Wikipedia. So we can see from that, most people do not like the smart meters. That's something interesting. So why? If we look into detail what people are complaining about, so the main reason they are complaining about the smart meter is the health problem. So that is basically because of the wireless mechanism for the transmit data. And so the wireless will cause the microwave radiation, and the people think that will damage their health. And some other reason people said smart meters are bad are the costs. So people think that to install the smart meter is expensive, and also to run the smart grid, the network of the smart meter, maybe also be expensive. So the result is people think that installing smart meter will cost more. And some other potential risks, fire risks, I will not expand that. And what I will be focusing on this talk is the privacy. So I will give some more precise definition of the problem here. So remember what I said before, smart meter is something that can record the data with a pretty high frequency. So I listed here. The granularity here for the smart meter can be minutes or seconds. So that is basically what people are concerned about. Oh, sorry, I missed something. So we call this the series of data with the 1 minute or 1 second frequency. We call it load profile. And here's the example of the load profile here. I think it may be clear enough. I will say something. So from this figure, we can see it's a load profile for about 3 days. And from this figure, we can see almost every day from approximate 11 p.m. to the other day in the morning to the 6 a.m., we can see the electricity load is always low at that time period. So can anyone have some idea. So what happens for the resident at the house at that time period of time?
I think they're sleeping.
Yeah, definitely. So it's just caused by people are sleeping at that time period of time. And the other thing we can observe from this load profile is there are some peaks here. So we can guess that they are caused by some energy maybe consuming appliances. So maybe they are cooking or maybe they are taking the shower. We know that water heater is really cost a lot of energy here.
I have a question.
Mm-hmm.
So because this is such a concern, but this thing, I mean this graph that you're showing, this has been going on for like many years, ever since the first Samuel Insull, when he first built his electric company, the Chicago Edison, something like that. This has been going on for many years. So okay. Is it because people are more aware now that this is happening and that's why they're feeling privacy is an issue now, or?
I don't know exactly what the...
Because he was measuring, this is how he was doing his pricing costs, was that he was measuring this, seeing the frequencies on, and I guess he was accumulating people's data or something on how they use electricity.
Yes,
so
how they use electricity, but I guess for the previous data, the granularity cannot be such small, right? So this is for every 1 second we record an electricity load here. Is that for the previous data? I'm not sure.
He was controlling, eventually. So I was just kind of curious if people are becoming more aware with
I guess
privacy.
I didn't mention clearly. So this is just the electricity usage for one house at this period of time for 3 days.
Yeah.
I guess what you said is not for one house, right?
No, he was measuring he was controlling a monopoly. So he controlled residential, he controlled businesses, and he was measuring everything.
Okay.
Like this. And I was just kind of curious. I guess my curiosity is if people are getting more aware of this issue, and that's why they feel privacy is an issue when this has been happening for many years.
Okay,
kind of thing,
I got your idea. I'm not pretty sure what happened in the past, but actually, yes, people are really concerned about that in the recent days. Okay, so at least for this figure, we can know something that's when people are sleeping or when they are cooking or something. But the question is, can we learn more about that? And unfortunately, so the answer is yes. We can get something like in this figure, so we can guess from this peak it's caused by a dryer or something it's caused by the heater from the TV. So to get this information, there's a method called the Non-Intrusive Load Monitoring method. So basically, the two main steps for this method is first, it's try to detect the load change event. So we call it a load change event when the current load is different from the previous load. So remember that the granularity of the data is just 1 second data. So it's just the load from the previous second. And then the second step is they try to match the load difference with some known appliance profile. So that is something we can get from the internet. I will give you an example of this detection. So first, from this figure, this is the load profile, so we can see that at 1 second, the electricity curve jumps up to the amount of 40 watts. And maybe we know that there's a bulb which takes the power of 40 watts at this house. So we say this is a match. And the guess we can make is this jump in the load profile is probably caused by the bulb is turned on. So you can see that from the load profile, we can know a lot of things. So actually, we can know pretty precise information of the appliances usage in the house. And because of currently in the nowadays, so people's behavior are more or less related to the electricity appliances. So if we can know all of the behavior of the appliances, there's no privacy of the person at home at all, right? So we are trying to hide this detection. We try to prevent this detection. To do that, we have a method called battery-based load hiding. So this is the picture of the meter and utility company and also your house. So the meter will record your usage in the house and transmit it to the utility company. And basically, the battery-based load hiding method means that we want to employ a battery to partially supply to the net demand. We call it DT in the house, and so it will use the battery to partially support the house to alter the external load. So we call it ET. This is something can be seen by the smart meter and also the utility company. So we have the equation here, ET equals DT plus BT, because all the energy must be used. So from this method, I think one ideal method we can think about is we can try to make everything flat. So remember that in the previous several slides, I have said there's a non-monitoring so I think I should show the slides. So this is a non-intrusive load monitoring method. So from this method, what we can do is the first step of this method is we need to find the load change event. So that's something we want to prevent the attacker know. And basically we want the battery to do such things. So let me give some name notation of that things. So we call it d prime t. It's the derivative of the demand load. So what we want to do is we want to use the battery to let people know less of dt or d prime t from et, which is the things which can be seen from the utility company. So one ideal approach, I think most people can think about this, we just try to make the output load, the ET, to be flat forever. So that is possible actually. So we can make it the ET always to be the average of the usage for 1 day or for 1 month. It is possible. And it sounds good, right? But there's one problem here. So it is infeasible because we need a really, really large battery. I'm not really sure whether we can get such a battery, but actually battery is really expensive. And I guess most people are not willing to pay such a lot of money just for privacy. So we must have some limit for the battery here. And in our settings, we say that so there's some capacity limit of the battery. So the battery cannot be always charged to full. The upper bound safe limit of the battery state is 90%, and the lower bound is 20% for the battery. And also there should be a limit charge or discharge rate from the battery. So we call it beta C and beta D, and we are assuming that these two numbers are the same. So now the problem becomes that we have such a limited battery and we have the load profile. So what we can do with such things? So in the rest of this talk, I will first introduce two existing methods, and then we'll propose our method, and I will show the experiment results. So first existing method is called the best effort method. So the basic idea of this method is it tries to avoid changing the external load whenever possible. And so to do this, what you can do is to charge or discharge the battery to make up the difference between the external load and the demand load, ET and the DT. And this is the detailed step for this algorithm. So there are just 4 cases when people have to change the external load. So that is when battery is full because we cannot further charge the battery. So we have to set the demand load to be like external load. So this is the 4 cases. It seems to be good, but the thing is we can still recover the load change event from this algorithm. So the reason is that so we can see from these slides. So no matter how we change it, it is always highly related to the actual demand load. We can see it's either equal to dt or to be dt plus or minus beta c or beta d. And the result is if we can observe 2 consecutive load changes in the external load in ET, then we can guess maybe the derivative of this 2 load is actually the actual demand. And from our experiment, we can show that the guess is pretty accurate. I will show the experiment result later. And here I give an example of the output of the best effort algorithm. So the upper figure is the actual load profile, and the bottom figure is the results provided from the best effort algorithm. We can see this in the big circle. It's the blue one. I think maybe it's not really clear, but we can see that there's a slope there, and actually the shape of the slope is exactly the same in these two figures, although the height is not at the same level. And also in the green circle, there's a jump, so the value of jump is also exactly the same in these two figures. So that's what we can recover from this algorithm. And I will begin to say about the other algorithm. So we call it Non-Intrusive Load Leveling algorithm. It's NILL algorithm. This algorithm is proposed in the 2011 in the CCS conference. So what it wants to do is it wants to set 3 states, and in each state, it tries to maintain a stable load for each state. So first is the stable state. For the stable state, it wants to guess what the average load in the near future will be. So in this algorithm, it mainly wants to stay at the stable state as long as possible. But if it can't, then there are two other states. So the high recovery state, that is because when the battery is over, it is discharged to almost empty. So we have to. Sorry, I got it wrong. Yes, if the battery is almost full, we have to discharge the battery. So at that time, we cannot keep the output load still at the stable state level. So we have to set the output load to be slightly lower than the demand load, so as to discharge the battery. There's a third state, we call it low recovery state. So in this state, this is caused by the battery may be empty, and we have to recharge the battery. So in this state, they set the output load, external load, to be the maximum charge rate, which is beta C. So I should say that this algorithm works actually pretty well if we have a large battery. But the thing is, in our setting, we do not have a large enough battery. So then here's the problem. If the battery is not that large, then this algorithm will leak the actual load when there's a high jump. We call it a peaks here. So the definition of the peaks is the peaks are the events that the demand is too high. And if we fully discharge the battery, we still cannot maintain the constant external load. So this is the load in the 3 states. And so we can see that the peaks will happen in these 2 cases. So ET equals to DT plus beta D if the battery still can be discharged. But the battery cannot. If the battery cannot be discharged, then the external load has to be equal to the demand load. So ET will equal to DT at this time. We say that if we can see 2 load change events, we can see 2 consecutive peaks, then we can recover the 2 demand load at this 2 point of time, and then we can recover load change events. So here's also an example. So in this example, we have the battery which the capacity of the battery is 0.5 kilowatt hour. It's not a small battery. It's actually, I remember the cost of that battery is around $100. So for this battery, we can see that in the bottom figure, this is the output of the NILL algorithm. We can see in these blue circles, the shape of the output load is exactly the same of the shape of the demand load, which is in the upper figure here. Okay, so now we have introduced two algorithms, and they are all not secure. So we can recover the load change event. So then we can find the behavior of the appliances. And next, I will present our method. So we call it a stepping method. So here, the idea of the stepping method is we want the quantization. So that means that we want the external load to be some integers plus beta. So beta here can be some arbitrary number. We just want to map the demand load to some certain number of constant value. So here the equation ET equals to HT times beta. So HT is always takes the integer value, and we want to choose beta to be the largest possible value. So this should be some value based on battery. And we say beta should be the smaller one of beta C and beta D. So I will give you the reason. So here, if we now observe a demand load at this level, and if the battery is already empty, so it cannot. If the battery is full, so it cannot be. If the battery is full, so we cannot even charge the battery. Is that the case? Oh, I guess I got something. Yeah, I messed up something. So in this case, we should say that if we observe a load at this level, and if we also know that. So if we have to charge battery at this level. So that means that battery may be empty at this time. So because we want the quantization, there are two possible values for this level of this value of input. So the output can be either 1 beta or 2 beta. But because the battery is empty, so we cannot discharge the battery. So the output has to be 2 beta. So that means that beta should be at least smaller than the max charge rate. So similarly, we can also get the idea if this point is around the 2 beta, then we have to set beta to be smaller than the max discharge rate, that is beta D. So beta should be the smaller one of beta C and beta D. Because of the mechanism here, we have another point here. So the only two possible output value of this input is 2 beta or 3 beta. Because of our mechanism, what we only need to decide is whether we need to charge or discharge the battery. So we set a charging signal here, ST. So that means that this algorithm actually is just controlled by this signal. So actually, we will give 4 different algorithms for this framework. So the first two we'll all call them lazy stepping, because for this algorithm we want to maintain the external load unchanged as long as possible. So that means it will only be changed when the battery is full, battery is low, or the demand load is too high or too low, so that we cannot keep the previous load. And there's 2 different versions of that algorithm. So in LS1, so we call it lazy stepping 1. So ST, this is the charging signal. It will be set to 1 if the battery is below half. So at that time we want to charge the battery. Or we have another version of that. So when when ET has to be changed, we set ST randomly to 0 or 1. This is one method we proposed, and this is already 2. So the third is lazy charging. So the idea is we want to maintain the ST unchanged. So we just keep charging the battery or discharge the battery until the battery is either too high or too low. And the third method, it's the fourth method, sorry. We just randomly select to charge or discharge battery, but we select a random number based on the battery state. So I will first give you some privacy analysis on the stepping algorithm. So here I would argue that one can always obtain some degree of privacy guarantee. That is because the observer's uncertainty is always 2 beta. So we can see in the, if we observe the blue point, we cannot observe the blue point. If we observe the external load to be 2 beta, we cannot determine whether it's from this red point or this blue point. So the uncertainty is 2 beta. And even if the attacker can know that whether the battery is charging or not, so that means that if the attacker knows, so if we say that the external load is 2 beta, and the attacker knows that now we are charging the battery, so he can only say that the demand load will be between 2 beta and 3 beta, but he cannot tell the exact value from our algorithm. So the uncertainty here is still beta. And if so that means that we cannot learn the accurate load change event. And here is also an example of our algorithm. You can see the output looks fine, so there's not much information we can know. We did some experiments. So first, I will introduce the set of the data set we are using. So we use 2 sets of data set. The first set is 1 second resolution data set. So the granularity is just 1 second. And this is collected in 4 houses and apartments in the United States. And we also use another set of data set. It is with 1 minute resolution. So it is from a study published on the UK Data Archive, and including the data measured in 1 minute resolution in 22 dwelling over 2 years. So we have a lot of data in this data set, and we just choose 6 longest consecutive data to do our experiment. And remember, we have some limited battery settings. We have some limited battery here. So in our experiment, we also limited the capacity of the battery. We measured the effect of the three algorithm on the battery with different sizes. So capacity of the battery ranges from 0.1 kilowatt hour to 1.2 kilowatt hour. And we always assume beta C equals to beta T, so the battery can charge or discharge with the same maximum rate. And we say the max discharge rate is 1C, so that means if a full battery is discharged at its maximum rate, it will be discharged empty in 1 hour. So for example, if we have a battery which has the capacity of 0.5 kilowatt hour, then in every second what it can be charged is just 0.5 kilowatts second. So here's the results for the NILL algorithm and the best effort algorithm. So I have already introduced how we can attack the result of these 2 algorithms, and here we show the result, how successful the attacks are. The denominator here is the number of events we detected, and the numerator is how many of them are accurate. So we can see from this table that our attack is pretty accurate here. So there's a difference for the upper side and the bottom side of this table, because for the 1 minute data set, so this is just the event detected per day. So the 1 minute data set, the length of that data set is 60 times shorter than the 1 second data set. So we can see the number of here is smaller. Okay. So I will introduce something here. I also want to measure our method, the stepping method. But the thing is, the stepping algorithm does not have similar vulnerability. So we cannot know the load change event from our method. So how can we measure that? Here we use something called mutual information. I won't go into the details of this method. I just put the formula here. So basically what the mutual information measures is the to what extent knowing one of the two variables can reduce the uncertainty about the another. So this is what mutual information do. And what we need to know is if the two random variables x, y are independent, then the mutual information is 0. And alternatively, if they are highly independent, then this value can be higher. I give you some reason why the information is 0 here, because if it is independent, then we know the probability of x times probability of y will equal to probability of xy. So we can get the log of this since it will be 0, so the information here will be 0 here. This is the reason why x, y are independent, the mutual information is 0. So in our experiment, we want to measure we did three sets of different measurements. So first we want to measure the mutual information between E prime and D prime. So here E prime and D prime are the derivative of the external load and the demand load. So for the other set of measurement, we try to get the mutual information between, we call it the binary version of the derivative mutual information measurement. So here we can see that we just do some pre-processing of our data. So if we have the load change event in the demand data is larger than 20 watts, we say that the B is 1, otherwise we set it to be 0. And also we do the same thing for the external load. So for this measurement, what we want to see is to what extent the information of a load change in E prime will correlated to a load change occurs in DT. Here we don't care about the value of the load change. We just want to see whether a load change will cause the load change in DT, whether it will cause a load change in ET. And we do another experiment. So here we use the Markov model. I guess I need to give you some introduction of what is Markov chain. So I put it here. So Markov chain is a mathematical system that can undergo transition from one state to another. And the main point of the Markov chain is its memorylessness. So that means the next state only depends on the current state, and it's not depends on the sequence of events that preceded it. So here's the formal equation here. We can see the probability of xn plus 1 is just based on xn. So we want to measure the mutual information of the Markov chain, because actually we know that the load power should be dependent on the previous one. So in the first set of measurement, we are assuming they are totally independent. So that's not correct. And here's some results we got from our experiments. So we can see from the results, so this is the mutual information. Remember that the smaller values means we get better results. So we can see here, our method is the right 4 bars. So the green is not good enough, but the others is good. This is the measurement of the, directly puts the mutual information on D prime and E prime. The battery setting is 0.5 kilowatt hour. We can see our result is better here. And for the binary version, one interesting, we can also see that our method is good, but the interesting thing is the random charging methods outperform the other methods pretty much. So I think the reason for that is for the random charging, whether to charge or not is just based on the battery state, but not based on the demand load or the external load. So the dependency will be smaller on that method. So we can see here the LS1 and LS2 are also good. It also outperform all the other methods except just the random charging. And for the binary version, it is more meaningful and the result is more clear. So all of our stepping algorithm outperform the best effort and the NILL algorithm here. So this can give us the results. The dependency between the load events are significantly weakened by our method, the stepping method. Okay. So lastly, we do some interesting experiments. The thing is, we know the battery expensive. So we also know that people mostly are not willing to pay that much money just for privacy issues. And we get one example here. So a 0.5 kilowatt hour battery will cost $100, and a larger battery, of course, will cost more. So we want to compare to gain similar privacy level, how large battery we should use for each algorithm. We use the mutual information here for the criteria. So the mutual information of over the Markov Chain model. And so here is the result. We can see from here that if we use the stepping algorithm, then for average we can use with that. Sorry, not for average. So we can use that small battery to get such a mutual information value. And if we want to get the similar privacy, so if we want to get the mutual information value close to that, for the best effort algorithm, for the 1 second data set, the average size of battery will be 1.4 times larger. And for the 1 minute data set, the battery will be about 2 times larger for the battery in the LS2. And for the NILL method, the battery will be even larger. So from the experiment, we can know that our stepping algorithm can obtain some good privacy protection with a smaller battery, and also, so that means a lower cost. Okay, so that's the end of my talk. Any questions? Okay.
Could you go back to the slide with the Markov chain model?
Do you know this? Do you mean this?
Yes. Actually, maybe one more forward, because you take one step between the values of E and D. So go one forward, please.
Okay.
Thank you. So you have one step between the values of E and
E prime and D prime.
Yes. So, but your Markov model is memoryless, and it works. The random charging algorithm seems to work very well because the decision to charge is based on the battery state. Yes. Well, the battery state is also based on the history of its usage, so maybe more steps backwards in times would reveal that.
That's true, but it's less related. But for the other method, they are more related to the previous state.
Okay, so
it's
best for now.
It's kind of cheating because the random charging is just based on the battery, and the battery it should be based on a long period of history, so we cannot know that.
Okay, thank you.
Maybe I'm missing something because the current in the houses is AC current, the battery is DC current.
Yes.
It is not just the price of the battery, so am I missing something, or how are they going to use the battery, not just connecting the battery?
It should be some techniques to transform the AC to DC, but we didn't do that just.
Yeah, that I'm saying that the cost is not just the battery.
You mean the cost of the transmission, there will be some energy loss, right?
Because there are a lot of integration of other systems, so
That's true.
Yeah.
We didn't consider that because we want to compare it with the previous one, and the previous one didn't consider that. If we do that, it's really hard to say, and it's much more complicated.
yeah, that's what I think. Thanks.
Okay.
So, is this purely for the reasons which the electrical company are going to profile you, or is there a reason? Is there another reason other than the profiling aspect of it?
Sorry, say it again.
As in the method that you, rather the whole way, the method that you implement, where you should not be able to detect the spikes and the troughs and the changes in your electrical usage. Is it purely to prevent the electrical company from detecting those things and building a profile about you?
No,
or-
we are not preventing electricity company from knowing that. So if it's just the electricity company will know that, that's fine. If we are assuming they are secure, so nobody else will get the data, that's fine. Actually, we cannot always make sure that, right? So it is some possibility maybe this data may be leaked to some bad guys. So just for the electricity company, it's fine.
I mean, have you seen such a situation? Because every kind of data has a possibility of being leaked. So
Yes, so that's what we are concerning. It may be leaked. It cannot be totally be secure.
thank you.
Any other questions?